Good morning, everyone. I hope everyone's doing well. Today, we actually have our last video notes for the semester, our last lesson of the semester as well. On Thursday, we'll be completing fluency test number 8. And that's it. That's the end of the semester. So today we are on page 541 in the book. We are looking at modeling periodic phenomena. We're going to use the sine and cosine functions in some real-life application here. So here's the first problem. You can take a second and read the situation here. What's happening is an engineer has been asked to create a Ferris wheel, and here are the dimensions of the Ferris wheel. It's 100 feet total tall from the ground to the top, and the diameter of the wheel is only 88 feet. Okay. It also tells us this, that 60 seconds is 1 revolution. And it tells us the direction is counterclockwise. So pretty important stuff, okay? Let's talk about this first question. Number 1, it says he wants to write a function that models the motion of the Ferris wheel. He's going to start by looking at point A, and we want to know the height. So if we go back to this picture here, if I look at point A right there, we want to be able to determine the height. Well, if we know the diameter is 88 feet, then we know that this distance here is 44 feet, and this distance here is also 44 feet. Those are both radii, right? The distance from the center to the edge right there is 44 feet. Okay, we also know that if the total height of the Ferris wheel is 100 feet and the diameter is only 88 feet, that leaves this little space right here as 12 feet. So if I'm starting with person A, at point A, the height of that is the 44 feet plus the 12 feet, which gives us 56 feet. All right. Now, here's what we want to do. Suppose that person is at point A and starts spinning, okay? Now, this isn't an accident. Think about the y-axis right here and right here. Point A is right where we started on the unit circle, and we're rotating in the same direction as well. Now, it takes 60 seconds to get around. Look at the breakdown of the time up here. It's every 15 seconds. And 60 seconds to get around means that it's 15 seconds for every quarter turn, right? So, or you can start there. You can go 30 seconds straight across and then start breaking that down. So at point B right here, which is going to be 15 seconds later, right? The height, we can find the height there. Point C right here is going to be 30 seconds into the spin. Point D down here is going to be 45 seconds in. And after 60 seconds, you're back here at point A. So you're at point A at 0 seconds and at 60 seconds, okay? So let's start putting this in the table. At 0 seconds, we already said we're at 56 feet, okay? After 15 seconds, we're up at 100 feet. So 15 seconds, we're at the tip top, which is 100. After 30 seconds, we're back over at point C. That has the same height as A, so 56. 45 seconds, we're down the bottom D. That's the lowest point. That's only 12 feet off the ground. 60 seconds, we're back to where we started from, 56 feet. And you can see we can keep this going. Let's go back to 75. 75, remember our arrows that show rotation here. At 75 seconds, I'm back to point B, right? Straight up and down, so that's a height of 100. After 90 seconds, I'm back to 56 feet. 105 seconds, I'm back down to point D, which is 12 feet off the ground. And after 2 minutes, I'm back to where I started again. That's point A, which has a height of 56 feet. All right. So we can see a pattern here that the heights start to repeat every 60 seconds. Thus, this is a periodic function, right? So that's why this is a good application of our sine and cosine curves. All right, so let's do this now. Now it wants us to take all those points and put them on a graph here. All right, so we'll plot these as best we can. I'm going to go back and forth here. I'm looking at the table on another screen, so if you need to look back at this, you can. So at 0 seconds, we're up at a height of 56 feet. So 56 is right about there. Okay. After that, 15 seconds, we're at a height of 100. So we're going by tens down here on the x-axis. So 15 is right in between the first and second tick mark, and we're up at 100. After that 30 seconds, we're back at 56. Okay. After 45 seconds, we're at the lowest we can go, 12, which is just right above there. 60 seconds, we're back to 56. After 75 seconds, we're back up to 100. 90 seconds, back to 56. 105 seconds, back down to 12. And after 2 minutes, 120 seconds, we're back where we started to point A, which is 56 seconds. Now, when we did this table, we did these quarter points up here, right? The quarter of the period. That's because those are nice Y values. In this graph, there are thousands of points, right? There's a point at 1 second, 2 seconds, 3 seconds, 4, all the way up to 15 seconds, and then 16 seconds, 17 seconds. So the curve would be what we've been graphing these last few days. Now, we're only using the key points to graph this, but if we considered every point on the curve, we'd get this. We're going down in height, we're going up in height, going down in height. So as time goes on, our height is fluctuating up and down. Thus, it's a periodic function. Now, what we want to do in number 9 is come up with an equation. Now, it's telling us which function it wants here. It wants sine, okay? So we're going to say f of t equals, and what I want to point out to you here is that there are a lot of options, okay? Right here, I see a sine curve, one full period. Remember, when I come up with the equation, I need one full period. I also see another sine curve here. Now, you could use this sine curve if you want to. The thing about this sine curve is it has a phase shift, right? We'd have to move this thing to the right 60. So you're going to add an h value into your equation. I don't want to do that if I don't have to. If I didn't tell you to use a sine curve, you could have used a cosine curve. I see a cosine curve, one period of a cosine curve right there. So you could have described this with the cosine curve. Again, the cosine would have a phase shift to the right, and that makes the equation a little bit more complicated. I'm going to use this first period of the sine curve I see. I'm going to use this because this does not have any phase shift left and right. The x value starts at 0, which means I don't have to have an h value in, which I like. All right, so let's go back. Amplitude. If I look at the midline here, okay, sketch that in here real fast. This is the highest point up here is 100. The lowest point here is 12. So just like on the x-axis, if I want to find halfway between 100 and 12, I add those up, which is 112, and divide by 2, I get a midline of 56. Now, the midline is important because it helps me find my amplitude. The distance between 56 and the very top of this graph, or the very bottom, is 44. So my amplitude is my a value out front is 44. Okay, sine of. Now I've got to go over here and find my b value. Now remember this little formula, period equals 2 pi divided by b. We've used this a lot. Usually I give you the b value and you use it to find the period. In this type of problem though, it's working backwards. I'm giving you the period, 60 seconds, and you've got to work backwards to find your b value. So the easiest way to do this is to put a 1 under 60 and do that cross multiplication. 60 times b is 60b. 2 pi times 1 is 2 pi. Divide both sides by 60 and then simplify, and you get a b value of pi over 30, which is what goes right here in your equation. All right. Now the t value is here. I don't need an h because we said we're picking the piece of the period of the sine curve that has no horizontal shift, no phase shift left or right. And then the k value here. Now in my notes I used a c and a d here instead of h and k. It's the same thing. So this k value here should be my midline, which is plus 56. And there it is. That is our function that represents this curve, and the curve which represents the Ferris wheel going up and up. Okay, now a few key skills to know here. What if we wanted to check our answer here? Number 10 says, how can you check the equation is this equation right here is reasonable. So Easiest way is to take out your calculator. Now, Desmos we're going to use here in a second. You could also use your calculator. And we're going to type some x values in, or some t values in. First thing you have to do here, though, is on your calculator, hit the mode button. It's at the very top of your calculator. And you've got to go and make sure that you're in radian mode. So I think it's 3 lines down. You'll see options to be in degrees or radians. Because back here in our equation we used 2 pi, we have to be in radian mode. Okay, so highlight radians, hit enter, and then if you exit out of that, you're good to go. So what this is asking for, this function is asking for a time input, and it will spit out the height. So one way we can check that this equation is correct is to plug in a t value we know the height to. So for example, if I plug in 15 seconds, all right, this is what you should type in the calculator, 44. Move this over just a little bit here. Okay, so 44 sine of pi. Actually, I'm going to move this down. I'm running out of room. So f of 15, what you'll type in the calculator is the sine of pi divided by 30. Now you want to multiply that by 15 and then add 56. So if you type in that right side, just how you see it, what you'll get what you should see is right here, 100 feet. Now you could have plugged in any of the x values there, but I chose to plug in 15 to check to see if it was 100. So if you wanted to find the height after 32 seconds, right? So f of 32 is what you're going to type in. This is 44 sine of pi divided by 30. Now times 32 seconds plus 56. All right, so I don't have my calculator here. Let me see if I can find it really quickly here. So if you want to take a second, pause the video even, and try to type that in to your calculator, see if you can get the correct number. I'll do it here as well on mine. Again, I'm checking my mode to make sure I'm in radian mode. And if I type in 44 sine of pi divided by 30 times 32 seconds, and then add 56, you should get a height of approximately, so the height after 32 seconds should be approximately 46.85 feet. All right, now I can check that to make sure that makes sense. If I look at my table here, if I look at the time between 30 and 45 seconds, right? At 30 seconds, I'm at 56 feet, so it makes sense for 2 seconds later to be a little bit lower, right? Between 30 and 45 seconds, I'm on my way down from 56 feet to 12 feet. So for 32 feet to be a height of 46.85 feet makes sense. All right, it's a good way, useful way to use our calculator. Now, let's look at something else we can do with our calculator. Now, we're going to show you this on Desmos. I'm going to show you this on Desmos because I don't have the calculator on my iPad, but you don't have to use Desmos. This is a skill we've done a few times this year, so you can do it whichever way you'd like. What we want to do is, so we'll read this number 15 here. The Sky Wheel will be a part of an amusement park that has several pine trees that are 80 feet tall. Tyrell wants to know the times when the car will be above the height of the treetops. So what we want to know is, when will this Ferris wheel be above 80 feet? All right, so the equation we're going to solve here is this. 80, that's the height now, equals our equation, 44 sine of pi divided by 30 t. Change that, doesn't look like a t. T, that's no better. T plus, and then we have 56. Okay, so that's the equation. Now, right now we don't have the algebraic skills to solve this equation for t. Okay, so we're going to do it a different way. We're going to use it using technology. So on your calculator, or on Desmos. Again, you should be in radian mode, and I'll show you in Desmos how to make sure you're in radian mode. We want to do that old thing where we type one side of the equation into y1 and the other side of the equation into y2, and then look for the t values, which in this case are the x. All right. So if you're using the ti, go ahead and type it in. Make sure, again, that you're in radians. If you're using Desmos, I'll show you what you should see here. Okay, so here I have y equals our function up top. Now, when you type these in, it's pretty straightforward. You can, when you want a sine function, if you go to ABC, you can just type in sin, and then it knows you're talking about sine. You can use parentheses to add things in the middle there. And then everything else, when you do division, it automatically puts it into a fraction. So like 3 divided by, x, it puts it into a fraction for you. All right, so line 1 here, I have my function. In line 2, I'm going to put 80 because I want to know where the height of this function gets to 80. Now, on Desmos, you have to adjust your window. On your TI, you have to adjust the window. Here, it's a little bit easier. I can pinch and zoom. If you're on the TI, you might want to do zoom fit, right? Remember, the zoom fit works well if you set your X and Y min. So the X min here would make sense to be 0. The X max, you can make that 120, right? That would be two revolutions around the Ferris wheel. So you want to maybe do zoom fit if you're on a TI. If you're on Desmos here, we can kind of zoom out here a little bit and start to see our graph. So there it is. You can see it goes up to a height of 100. Looks just like the graph we made by hand. Now, if I want to find where this blue line hits it, on Desmos, I can just kind of touch on the points. Now, if you're doing the TI, you have to do, after you do zoom fit, you have to do second calc intersect. And you'll have to do this a few times until you get a few different x values. Now, you don't have to do it a ton of times because once you find 1 or 2, you know the period and you know the fractions of the period, so you can follow the pattern. But let's go back to Desmos here. All right, so if I look at this first point, I want to know when it hits 80 feet right now. So right there, it's going to hit 80 feet at 5.5 seconds. So it says round in the nearest tenth. So time is going to be 5.5 seconds. And it just wants the first 2 complete rotations here. I just saw that. So the X max of 120 there is the best option if you're using the TI. So the first time it hits 80 feet is 5.5 seconds. And this wants the time at the same height of the treetop, so we don't want any kind of intervals. We just want the times. So 5.5 seconds. I go back here. The next time it hits 80 is right there at 24.5 seconds. And again, if you're doing this on the TI, you're doing second calc intersect. You're moving the cursor a little bit. You have to do it once for the first point we did, once for the next point. You'll have to move the cursor closer and closer to these points of intersections. The next point here is 65.5. And the next time after that is 84.5. You can try that on your own, 84.5 seconds. So what we've done here with it, once we've gotten the function, we've done 2 things now with it. We've used the calculator, just plug in values, plug in the next value to find a y. And we've also used the calculator or Desmos or technology to find x values, where we graph both sides of the equation. And on Desmos, just click the points of intersection, or on the TI, do second calc intersect. I don't care which way you do it, they both work well. And that's it for today. So your homework is 35-1, lesson 35-1 homework. As always, these answers are on Schoology. When you're done, submit this to Schoology. And also, a little bit unique today, if you want, like I said earlier, fluency test number 8 is going to be on Thursday, but I've already posted it. So if you want to, you can start fluency test 8. It's not due until Thursday this week, but if you want to get a head start, you may. It's up there ready to go. It's made up of 2 things, a written portion and multiple choice. If you want, that's a little bit better English. If you want, start fluency test number 8. All right? As always, email me with any questions. Stop by my office hour with any